Hello, everyone. Today I want to talk about two papers in the realm of distillation. They're actually foundational to the paper that coined the term distillation, but back then it was referred to as model compression. So, the first paper that I want to talk about is called model compression. It coins the term model compression, and this is what's later known as distillation. And the second paper that I want to talk about builds on top of this, still doesn't coin the term distillation, but it kind of goes more into why it works. So I want to talk about these two papers since they're related. The first one's from 2006, and the second one is from 2013. So I'll start with model compression. I'll just go over high level overview and then go through some of the details that I learned. Okay. So model compression revolves around the accuracy efficiency trade off. This trade off is the idea that large models are more accurate, but they're also less practical, less applicable because they're less efficient. They're more computationally demanding. While small models, on the other hand, are more efficient, but they're also less accurate. So that's the trade off. Now, let me give you a situation that is actually quite common in machine learning. So, say we have labeled data, and say we also have a lot of unlabeled data, and we got, we achieved a large accurate model by training that architecture or ensemble or whatever on the labeled data. The question model compression tries to answer is, how do we take advantage of having a large accurate model as well as unused unlabeled data to train a smaller model? So what is done before model compression, or what can be done before this idea of model compression, is just training the smaller model on the same label data. But this doesn't achieve the same accuracy as the large accurate model. So how can we do something better than that, right? So what's happening when we train a large model on this unlabeled data? Well, the large model function is trying to approximate the function that emitted the data, the true underlying function. And when we do the same thing, we try to train a small model on the same unlabeled data, or the same labeled data, tries to do the same thing. It tries to model the data's true underlying function that emitted that data. But the smaller model is usually less accurate. But we now have a large, the large model's function, which is accurate. So what if instead of training the small model to approximate the data's true underlying function, what if we try to make the small model instead approximate the large model's function? So basically, instead of training the small model on the labeled data, what if we label the unlabeled data, and we can label the labeled data as well, with the large model, right? Because if we label the unlabeled data with the large model, now we have a data set that is emitted by the large model's function. And if we train the small model on this new data, then it will be approximating the large model's function instead of the true underlying function. So it's shown in this paper that it's more accurate to do that than train the small model directly on the labeled data. Now, why does this work? Well, this paper doesn't really go into it. It just shows that it works. And the next paper kind of goes more into the details of why this may work. But the important thing here is we have the small model approximate the large model rather than approximating the underlying function of the data. So that's model compression. Pretty straightforward. We train a small model to mimic a large model instead of training the small model on the original labeled data. So that is the gap. Let's see if there's anything else here I need to cover. Mimic the function by. So the paper shows this idea by the small model is a neural network and the large model is an ensemble. So the ensemble is accurate, trained on the original data. And then what happens is they label the unlabeled data with the ensemble. And then the neural network is trained on this data set. So the result is the neural network is able to achieve similar performance as the ensemble while being much smaller and faster, about 1,000 times smaller and faster. So why is that significant? So when we train the small model on the original data, we try to approximate the true underlying function, right? So this is small x. We're trying to approximate the true underlying function. And when we train the small model on the large model predictions, the data emitted by the large model, we're trying to approximate the large model's function. And this is shown to be more accurate. So why is this significant? Well, we are getting more accuracy while being the same efficiency. So if we kind of ignore the larger model for now, comparing the small model, same architecture, trained on the original data, comparing that to same architecture, small model, trained to mimic the large model's function, we have the same efficiency because it's the same parameters, same architecture, everything, but we're more accurate. So with the accuracy efficiency trade-off, we're becoming more accurate without trading off efficiency. So that's why it's pretty significant. So with that, I want to go into a little code example, and then I'll move on to the next paper. Okay, so now we're going into a little code snippet. It's not a reproduction of the paper, but it's the same idea applied. So we start with a simulated data set where we have labeled examples and we have unlabeled examples. And we train the ensemble on the labeled examples. And we get 95% accuracy. Now we trained a small model on the same data set, the original data set, labeled data set, and we get an accuracy about 93%. So there's a difference of about 2% accuracy between the ensemble and the neural network. So now we label the unlabeled data with the ensemble, and we train the small model on this new data set. And this is model compression. So we see that the accuracy improves to about 94.5%. So summary, ensemble is 95%. We train a small model on the original data set as well, and it's 93%. So there's a gap there between the large model and the small model. But when we have the small model mimic the ensemble rather than training it on the original labeled data set, by training it on the pseudo labels of the unlabeled data set that the ensemble provides, we get an accuracy much closer to the ensemble. Okay, so now I want to talk about the second paper called Do Deep Nets Really Need to Be Deep? And these build on top of the first paper, model compression. And it kind of goes into why model compression works. So let me start with how the paper opens up. So the main thing the paper revolves around is the idea that depth is not required for representational capacity. And they prove this because if a shallow network is able to accurately approximate the underlying function of the data through model compression, then it has enough representational capacity, and that means depth is not required for that. But maybe for now, depth is required for learning the underlying function, like how the large model does for model compression. So that's the main idea of the paper, that depth may be required for learning the function, but it's not required for representation. And they show this through model compression. But one more significant thing that this paper contributes is soft targets, the idea of soft targets. And it really sets the foundation for what is known as the original distillation paper. So I'll go into that now. So soft targets. So let's go over first how the previous model compression technique would work, and then we'll go into how soft targets would work. So let's say let's say we have multi-class classification problem between three classes. So we have a, let's say, a large model, and let's just do one example. So first, the large model would output raw scores of the three classes called logits. So we'll just do something like this. Okay. Then after that, we feed it through a softmax, and we get a probability distribution, P1, P2, P3, where P3 would be the highest one. And we label the unlabeled data. Like, let's say this is an unlabeled example, and this is model compression. We would label this with the large model as 0, 0, 1, because P3 is the most likely one. So we have now just labeled this unlabeled data. It is belonging to the third class. So that's how model compression works. This is how we label the unlabeled data with the large model. Now, how would we do soft targets? So soft targets is the idea of using the logits here instead of using these. So instead, we would try to have the small model mimic the raw scores, the logits of the large model, rather than training the small model on the pseudo labeled data. So that's the whole idea of soft targets. And we do this because it provides more information. And we'll go into why that case may be. So here's an example. Let's say we have raw scores, -10, 0, 10. This is for one instance. And then another instance, say we have 10, 20, 30. These are different raw scores, but if we feed it through softmax, we get the same probability distribution. So there's some information loss here because the large model learned to output certain logits as for certain cases, as opposed to other logits for different cases. But if we use the softmax, then we merge them into one case. So that would be information loss. And let's go into another example. The softmax raw scores are these values. Okay. And say the prediction of the smaller model is this. So this is the probability distribution from the large model, and this is the distribution outputted by a small model. This would be the loss that we feed the small model to learn to mimic the large model in this case. And we can see that all the weight would be in the largest class. That means the smaller model would mostly focus on getting that right, and it wouldn't really try to learn any differences between other classes. It's just mostly focused on that main class. So let's go over what would happen if we use raw scores instead of softmax, which in this case, the softmax target is also basically hard targets. It's closer to one-hot encoding, but it's not exactly there yet, but it's basically very close. So it's a hard target. But now let's look at a soft target. So with a soft target, we have logits, and we have logits for the small model, and we have logits for the large model. So these logits, if we were to softmax them, it would be these exact same, this softmax target and this prediction. So it's an equivalent situation. But now, since they're raw scores, we don't use cross entropy because it's not two distributions, it's just raw values. So we use MSE loss, mean squared error. And from this loss, we can see that the losses spread out more evenly across all three classes. So that means the small model being trained with soft targets instead of harder targets will learn more of the internal modeling of the large model. And that would lead to more information for the small model to learn. So that's why softmax, or that's why soft targets is important, and it really sets the stage for distillation. So now let's go over the result. The result is mostly this. So we already said that they proved that a shallow model is capable of representing what we used to think was too complex of a function for it to represent. So they already proved that. But there's a lot of other kind of analysis that they bring with the paper. So the first one, why does model compression perform better than training on the original data set? Now, they trained the shallow network without even using unlabeled data. So they did not do this predictions. They did not use the large model's predictions on unlabeled data to train the smaller model. Instead, they used the large model's predictions on the same original data set. So it's the same amount of data points. Yet still, the small model is able to be more accurate with model compression than training directly on the original data set. So why might that be? And it could be due to three things that they mentioned. The first one, label noise. So imagine a binary classification task where we have labels like this: star, circle, circle, circles, circles. Say humans are labeling these, right? And they're spread out like this. So we see a clear boundary between them. But let's say someone accidentally labels a circle here, it's supposed to be a circle, they label it a star. Well, the function the large model will learn will look something like this. And because of that, it would classify this closer to a 0 or to an O. And therefore, it would eliminate that label error. Okay. And then the other one we kind of touched on in model compression paper is that the teacher or the large model simplifies the function to learn for the student model, small model. And then lastly, uncertainty information. So when we have hard targets, it seems like we're certain that something is that thing. So for example, let's say we're classifying between dog, dog, wolf, and something like car, right? Now let's say there's something that looks like a dog and a wolf, wool, but it's actually a wolf. The hard target would look something like this, and it seems like we're certain that's a wolf, even if it looks very close to a dog. But what the large model would do with the raw scores is it would show more of classes that are similar and confusable. So, for example, maybe this would be a 5, the dog, and it would be like a 6 that it's a wolf, and then it would be like still like a 0 or a negative value that it's a car. Basically, with the raw scores, the dog and the wolf are close. And so the soft or targets provide uncertainty information. And that uncertainty is information for the small model. So there's more to learn with soft targets than with hard targets. So that's why model compression can perform better than training on the original data set, even if we don't use any extra unlabeled data. So another question, as accuracy of the teacher model increases, what happens to the student model accuracy? And they showed that it's basically linear as well. So let's say this is the teacher model's accuracy. And they showed that the student model's accuracy is basically linear as well. So that means as we improve the teacher model accuracy, when we do model compression on the same student, it will be more accurate as well. And it also means that with a more accurate teacher, we can get more efficient in the student with the same accuracy. So how is that the case? Well, let's say we have a less capable student over here, right? Let's say we're targeting something like 80% accuracy. Well, in order to get that 80% accuracy for this middle student, we would need this accuracy here for the teacher. But if we have a strong teacher, then we would, let's say we can achieve this accuracy here on this teacher. Then we can have an even more efficient student with the same 80% accuracy. And another thing is that the small model doesn't run out of capacity, or at least it's shown in the paper. It's not shown in the paper that it runs out of capacity. That means this continuously increases and it never flattens out. At least for the model and data they tried. So those are three important things that come with a student increasing linearly as the teacher's accuracy increases linearly. Yeah. So that is the main stuff behind this paper. It really does seem like this is distillation, and it basically is the same as distillation, but it's not coined as distillation yet. It's model compression. So I hope those two papers were fun to learn about, and I hope I explained it well. But yeah, that is model compression, and do deep nets really need to be deep?